Welcome to Royal Chemistry Pub, the YouTube channel. In this video, today we are going to see the mechanism of elimination reactions. Let us first take the E1 reaction. Let us consider the dehydration of tertiary butyl alcohol by corn sulfuric acid giving unsymmetrical dimethyl ethylene. Since the rate of the reaction depends only on the concentration of tertiary alcohol, it is called the E1 mechanism. It is also called as elimination unimolecular. You see, now you are seeing the reaction in the screen. So, the tertiary butanol, when it is treated with corn sulfuric acid, a water molecule is getting removed and you will get the unsymmetrical dimethyl ethylene. So the rate is directly proportional to the concentration of the substrate alone. That is why it is called as the first order reaction. The mechanism involves the combination of a proton with the alcohol molecule forming first an oxonium ion which dissociates later into a carbocation and water. So first this will form the oxonium ion. This is what called as the oxonium ion. So when the tertiary butanol, when it reacts with sulfuric acid, first it gives the oxonium ion like this, and this oxonium ion, after getting dissociated, it will gives this carbocation, what is obtained as the byproduct. The carbocation attracts to itself the electron pair from carbon-hydrogen bond of an adjacent carbon atom, and there is simultaneous liberation of a proton. Here you can see the carbocation structure, and this carbon actually attracts the electron pair between the adjacent carbon. Here this carbon and hydrogen, these two carbon and hydrogen atoms are joined together by a bond pair of electrons. When this carbon attracts this bond pair of electrons towards this, the hydrogen is getting removed from this species. So as a result, you will have a structure like this. Actually, the mechanism involves a two-step process. The first one involves a rate determining step involving the formation of a carbocation. This may be formed by ionization also. The ion rapidly loses a proton from the carbon to the base, which is solvent. This is nothing but the second step of the mechanism. So in the first step, it may be taken as the rate determining step, and the second step, which rapidly loses a proton from the carbon to the base. So many secondary and tertiary halides undergo this E1 type of elimination. Therefore, E1 elimination appears to be analogous to SN1 reaction, where also the rate determining step is the slow ionization of the alkyl halide. But the second step is different. While there is elimination of a proton from the carbon atom of the carbocation in E1 reaction, there is an attack of the nucleophile at the carbocation SN1 reaction. The picture is as shown in the screen. So here you are having the two possibilities, whereas you are having the only one structure. This is the first step, which may be called as the rate determining step, and this is the fast step. So here the reaction which prefers whether it goes through the E1 or it goes through the SN1 reaction. If it prefers to goes through the SN1 type, you will have butanol, an alcohol molecule is produced. Whereas if E1 reaction is preferred, instead of alcohol, you will have an alkene as the product. So from this, it is clear that the E1 and SN1 process are always competitive. The E1 reaction is most likely to predominate when the solvent is a poor nucleophile. For example, when it is having formic or acetic acids. Number two, the halide is on highly branched carbons. This also explains why in many of the SN1 reactions, an olefin formation is an important side reaction. This substitution reaction is favored by the presence of good nucleophiles, while strong bases which remove proton easily from the carbocation and favor elimination reactions. Now let us see the evidences of E1 mechanism. The first evidence is kinetic, and the reaction exhibits first order kinetics. The reaction rate is independent of the base concentration. If the reaction proceeds through E1 mechanism, it should involve the formation of a carbocation, and the behavior of carbocation should be independent of the nature of the leaving group. Thus, starting from tertiary butyl chloride, tertiary butyl bromide or tertiary butyl iodide, when there is competition between SN1 and E1 reaction, and when a mixture of olefin and alcohol should be formed, the composition of the products should be same independent of the starting materials, and this has been found to be the case. So, if the substrate prefers to go through the E1 mechanism, then 19% product is obtained, whereas if it prefers the SN1 path, then the yield will be 81%. So another criterion which may be applied is about the composition of the olefin mixture in cases where it is possible. With halides such as tertiary pentyl halide, E1 reaction tends to favor the most stable olefins, the most highly substituted one. So it is said that E1 elimination favors Sets-F rule. Again, the proportion of the two olefins is independent of the nature of the leaving group. This again means that a common intermediate, the carbocation, is involved in the eliminations. And the third evidence involves another feature of E1 reaction. It is the tendency of the carbocation to rearrange itself to give a more stable ion, and these have been formed in elimination reactions. For example, the carbocation from neopentyl iodide leads to predominantly to 2-methyl butene 2 through migration of a methyl group with its bonding pair of electrons from the beta to the alpha carbon, transforming an unstable primary carbocation to a stable tertiary carbocation. Elimination of a proton completes this reaction. So here you are having this, the first one is the unstable carbocation. So by means of migrating a proton, it transforms into a stable carbocation, which is shown here. So this involves the another evidence, which is the salient feature of the E1 reaction. So far we have seen how the E1 mechanism is getting executed. Now we will see the E2 reaction. So in order to explain the E2 reaction mechanism, let us consider the dehydrohalogenation of an alkyl halide induced by a base, that is a hydroxide ion. And here in the screen you can see this is the alkyl halide which reacts with the hydroxyl ion. You will have an alkene and water, and simultaneously the leaving group is getting departed from the substrate. So the kinetic studies have shown that in such elimination reactions, the reaction depends on the concentration of both the alkyl halide as well as the base. Because this is the concerted process, we can say that everything is happening in the similar step. It is a one-step process. So the rate determining step involves all the concentration of the substrate as well as the base. So if you write the rate rate equation for this reaction, then rate is directly proportional to the concentration of the substrate in the concentration of the base. Hence, the reaction is a bimolecular process and is abbreviated as E2. The mechanism involves the attack of the base OH minus, removal of a proton from the beta carbon, and the simultaneous formation of the double bond and loss of the halide ion from the alpha carbon atom. Everything happens in a single step. And here you are having the substrate. So the OH, when it attacks the carbon, it removes the base, and a water molecule is getting removed and the formation of a olefinic double bond is formed here. Therefore, the abstraction of a proton, formation of the double bond, and elimination of the halide ion are all simultaneous concerted process rather than stepwise process. And if you talk about the E1 reaction, where the mechanism proceeds through stepwise, that is, the first step is the rate determining step, and the second step is the formation of the product. But here everything happens in a single step. That is why this step is called as the concerted process. So there appears to be an analogy between E2 and SN2 reaction. So in the previous case, we compare the SN1 reaction to the E1 reaction. Similarly, here also we can compare the E2 reaction with the SN2 reaction. So in both the cases, the reactions are bimolecular and the process involved are simultaneously concerted process. In one, the product is an alkene. In another, it is an alcohol. Since E2 and SN2 reaction involve the same reagents, there is always a competition between the two, and in many cases, a desired substitution will more or less accompanied by elimination. Now let us see the evidences for the E2 mechanism. The evidences are as follows. Number one, the reaction displays a second order kinetics. Number two, stereochemical studies support the mechanism. So to achieve maximum overlap in the developing bond orbitals, the orbitals must all lie in one plane and the two groups eliminated, that is hydrogen and halogen, must be trans to each other across the central bond, which becomes the pi bond. Such an arrangement of groups is called trans-antiparallel or trans-periplanar. The entire process is known as trans-elimination. Now you are seeing how the plane, the X and H are trans to each other. Here you are having X, here you are having H, and these two planes are contrary to each other. So the term trans elimination refers to the position of the groups and not to the geometry of the resulting olefin. Only a few cases of cis coplanar elimination have been found in compounds for which the trans coplanar geometry is impossible. The trans elimination also occurs in the formation of a triple bonds as shown by elimination from cis and trans. So the product in both the cases is acetylene dicarboxylic acid. The trans isomer reacts about 50 times as fast as the cis compound. So kinetically, the process would be a second order since the formation of the carbon ion involves the base and the substrate, but the rate determining step would be the second one, which involves the loss of leaving group. The process can occur if the carbon ion is strongly stabilized and the leaving group is sufficiently poor that it will not be lost by E2 mechanism. So far we have seen the mechanism of E1 and E2 reaction, and we have also seen the evidences for the E1 and E2 mechanisms. The remaining things we will see in the next lecture. I am Dr. K. Rajarajan, Associate Professor and Head of the Department of Chemistry, Raja Sarfoji College, Tanjavur. Thank you very much.